Hello all, good morning. This is Dr. S. Subbalakshmi, an assistant professor in the Department of Mathematics, SNS College of Technology. This is a lecture video series on the course Differential Equations and Transforms, and we are on to the topic Green's Theorem. First of all, what is Green's Theorem? The Green's Theorem is an interrelationship between the line integral and the surface integral. Line integral means a single integral and the surface integral means double integral. So it is the interrelationship between the line integral and the surface integral. The statement goes like, if R is a closed region in the xy plane bounded by a simple closed curve C, and if m and n are continuous functions of x and y having continuous partial derivatives in R, then the integral over C m dx plus n dy is equal to double integral over the region R dou n by dou x minus dou n by dou y into dx dy. Here C is the curve traversed in the clockwise direction. This is the statement of the Green's theorem, wherein we have a curve C on the LHS and the region R on the RHS. We can notice that there is a curve C on the LHS and the region R on the RHS. Here we have two continuous functions m and n, and here we are having the partial derivatives dou n by dou x and dou m by dou y, where and the C is considered only to be in the anti-clockwise direction. So first of all, we will evaluate a function using Green's theorem. Evaluate by Green's theorem, integral over C xy plus x square into dx plus x square plus y squared into dy, where C is a square formed by the lines x is equal to 1, x is equal to minus 1, y is equal to 1 and y is equal to minus 1. So we have to draw a curve which contains all these as the boundaries. So how will that be? If x is equal to 1, it will be along, if x is equal to 1, it will be parallel to y-axis. If x is equal to minus 1, it will be parallel to y-axis here. If y is equal to 1, it will be parallel to x-axis, and y is equal to minus 1, it will be parallel to x-axis here. Likewise, we will draw the figure using the given condition. The solution to the given problem. Here we have the problem as integral over C xy plus x square dx plus x square plus y square dy. What will be the m and n? M is nothing but xy plus x square. What will be n? It is x square plus y square. These are your m and n's. How will be the limits of the function? X is equal to 1 to minus 1 and y is equal to 1 to minus 1. So using Green's theorem, what do we have? Using Green's theorem, we have integral over C is equal to double integral over R. This is what we knew from the Green's theorem. And here your m is xy plus x square and n is x square plus y square. Now we have to find the LHS using the RHS. So what is m? M is equal to xy plus x square. On integrating it with respect to y, we have x alone. What is n? It is x square plus y square. On integrating it with respect to x, we have 2x alone. So this is the thing we are going to substitute in the RHS of the equation of the Green's theorem. So on substituting it, you have 2x minus x dx dy. Within the limit, x is equal to 1 to minus 1 and y is equal to 1 to minus 1. So if x and y's limits are 1 to minus 1, it is x into dx dy. So on integrating it, you will have x squared by 2 within the limits minus 1 to 1 dy. On substituting the upper limit and the lower limit, it will be 1 by 2 minus of 1 by 2 into dy. 1 by 2 minus 1 by 2 is 0. Therefore, the value of the integral here is 0. So, integral over C on the boundary of the square is 0. This is what we found using Green's theorem. So, what have we done here? We have taken up the function here which have continuous functions like m and n, on the given function. We have taken it into account, and then what we have done, we have changed it over to a region R, and we have found the partial derivatives here, and then resubstituted it in the RHS of the Green's theorem, After resubstituting it and simplifying it, we have arrived at the solution for the given question for the line integral. So this is how we evaluate using Green's theorem. Just in this problem, we have just evaluated a problem with the line integral on the LHS with the surface integral on the RHS. We'll continue with this in the next problem as well. Thank you.